We'll come to the second topic of fiber optics, that is physics of light, that will just deal with the different characteristics of light. So the first one we'll look into are the laws of reflection, of which I think you have already done in physics. So let's just have a brief look at it. The first one, the incident ray, the reflected ray and the normal all at the point of incidence all lie in the same plane. The angle of incidence is equal to the angle of reflection. Looking at the diagram, you will see that over here, according to the first law, you will see over here, the incident ray, the normal and the reflected ray all lie in the same plane. Over here, the plane is the mirror. Now, in the second law, the angle of incidence is equal to the angle of reflection. So that is the laws of reflection. Now we come to the laws of refraction. The incident ray, the refracted ray and the normal to the interface of the two media at the point of incidence all lie on the same plane. The second one, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, and this is known as Snell's law of refraction. And this constant we will talk later on, which is also known as the refractive index. Okay, so according to laws of refraction, you will see over here the incident ray, the refracted ray, and this is the normal, all lie on the same plane in the interface between the two media. This is medium 1 and this is medium 2. So the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, and that is known as the refractive index. Okay, so those are the laws of refraction. Now we will come to the definition of refractive index and critical angle. These are just a brief description because you have already done in physics. Now the refractive index is defined as a ratio between the speed of light in vacuum, denoted by c, which is equal to 3 × 10 to the power 8 meters per second, and the speed of light in the medium, that is v, where mu is equal to c by v. Mu is known as the refractive index. Okay, mu is equal to c by v. This is its association as a definition of refractive index based on the speed of light in vacuum and speed of light in the medium. Then another definition, light rays propagate within different media at different velocities, and these media resist the light propagation with different strengths. The characteristic that describes this property of the medium is called refractive index. When you have whatever you have done in physics, you will see that different materials have different refractive index. What do these numbers indicate actually? These numbers indicate the strength that they are able to resist the penetration of light through them. Okay, so the ability of those materials to resist the penetration of light is a certain number, and that number is known as the refractive index. Refractive index of air is given as 1.003, which we take commonly as 1, water is 1.33, glass 1.4, quartz 1.46, diamond 2.42, silicon 3.4, and gallium arsenide is generally a semiconductor mainly used for the construction of fibers. So that is 3.64. Okay, so because you'll be using different light sources having different semiconductors, these are the different values of refractive index. Now we come to the definition of critical angle. Critical angle is the greatest angle at which a ray of light traveling in one transparent medium can strike the boundary between that medium and a second of lower refractive index without being totally reflected within the first medium. That means over here you know that when you're moving from a medium of higher refractive index to lower refractive index, what happens to the particular refracted ray? It tends to bend away from the normal. Okay, so when we move from higher refractive index to lower refractive index, the refracted ray bends away from the normal. So it keeps on bending away from the normal until the particular refracted ray, okay, will just graze the interface between the medium 1 and medium 2. When I say graze the interface, it will just lie at the boundary between medium 1 and medium 2. So at that particular point, that angle of incidence that creates that particular angle of refraction, that is known as the critical angle. The critical angle is defined as the angle of incidence that provides an angle of refraction of 90 degrees. Okay, so that means when the angle of refraction is 90 degrees along the line of separation between medium 1 and medium 2, that angle of incidence that creates that particular angle of refraction is known as the critical angle. So mathematically we can show that sine I by sine 90. So that means the angle of incidence, according to Snell's law, we have sine I by sine R is equal to a constant, right? Now over here sine IC by sine 90 is equal to 1 by mu, where we're taking that the angle of incidence as IC. That means IC creating the critical angle at that point, whereby the refractive index here is the angle that is created at the angle of refraction created is 90 degrees. This is equal to 1 by mu. So taking this mathematically, we have IC is equal to the critical angle is equal to sine inverse of 1 by mu, where mu is the refractive index of the denser medium, and 1 is generally taken that the rarer medium is air, thereby 1. Thereby you get the value of 1 here. Okay. Now, what is total internal reflection? Total internal reflection takes place at the boundary between two transparent media when a ray of light in medium of higher index of refraction approaches the other medium at an angle of incidence greater than the critical angle. Now, as we move from denser to rarer medium, okay, the angle of refraction moves away from the normal. As it keeps moving away from the normal, at a certain point of incidence, it will generate an angle of refraction that grazes the surface between the medium 1 and medium 2. For that particular refracted ray, the angle of incidence is known as the critical angle. However, if the critical angle increases more, if this angle of incidence increases more than the critical angle, so what will happen is the angle of the refracted ray will continue to bend. Okay, it continue to bend even after the interface also, thereby just as if it is coming back to its original medium, right? So at that point, what happens is the refracted ray comes back into the first medium, that's why it's known as total internal reflection. So that means as if it's everything, all the phenomenon is happening only in one single media. The phenomenon occurs if the angle of incidence is greater than a certain limiting angle called the critical angle. That is the how total internal reflection is caused. Now when you look over here, you will see, okay, so consider two media, denser to rarer. The incident light is the light source that is over here at the bottom. There, right at the bottom is a light source. Okay, so when the light source, here is a denser medium, consider this is water or some other media, this is air. So light is going from denser to rarer. So as you can see, it's moving away and away from the normal. At this point, what we have is that particular is known as the angle of incidence. Sorry, is a critical angle. This is your incidence angle. Okay, that means this will be particular your critical angle. Now this critical angle will create this reflected ray. This refracted ray. Right? Now if the critical angle continues to, if the angle of incidence continue to increase more than the critical angle, what happened? The ray is reflected back within the same medium. Here, the angle of refraction will move away, more away, thereby looks as if it's coming back into the first media. This is your phenomenon of total internal reflection. Now, total internal reflection can take place only when the two conditions are being met. That is, a light ray is in the more denser medium and approaching the less denser medium. That means the light ray is moving from denser to rarer medium. The angle of incidence for a light ray is greater than the so-called critical angle. That means the angle of incidence creating the total internal reflection will be greater than the critical angle. Okay. Now, over here I am giving you an assignment. Okay. So, based on mu equal to C by V, I want you to find the values of these problems. Okay, what will be the critical angle? What will be the, calculate the velocity of light within water. Okay, mu is equal to C by V. The refractive index of water is 1.33. The refractive index of diamond is 2.42. This is given. These are given. Use this. C is given. Find the value of velocity of light within that particular media. Okay. Find the critical angle of incidence of a transparent glass rod surrounded by air. When you see transparent rod, there is no values given over here. So do not think that you're going to give a theoretical explanation about this. No. The transparent glass rod surrounded by air, you know that the refractive index of glass is 1.5, air is 1. So find the critical angle using that formula which I have just given just now. Now look at this one, number 3. When light beam strikes a water-air boundary, calculate the critical angle of incidence. Light beam, even this. Some students I have seen, when you give questions like this, they tend to think that, okay, it's a theoretical question, no numbers are given, so they will answer theoretically, which makes no sense also. Okay, when I see, so over here, you know, the refractive index of water is 1.33, refractive index of air is 1. Find the critical angle for that particular phenomenon that takes place over there. Okay. Those assignments I am giving in the slides also, you have to do it in paper, and if classes start, you'll submit it to me on paper. If at all you do not have classes for quite some time due to this pandemic, what will happen? You will do it at home and submit it to me to PDF through WhatsApp. Now we will come to the next phenomenon of light, that is diffraction. Okay. What is diffraction? Diffraction refers to the phenomenon that occurs when a wave encounters an obstacle or a slit. Now, when light is when light is incident upon any surface that is not transparent, what do you see? The particular object or the particular opaque object will try to block away the light from its surface. But however, as you move from the corners of that object, you will see that light is able to move across the corners. That is why a shadow is created behind the object, right? Now, or a slit. Now, if you have a door which have holes in it, and you allow light, when light is incident upon that door, what will happen? The whole door will block the light. But however, that small aperture or hole present in that door will be able to allow the light to enter to it. So sometimes you'll see a beam of light entering through that particular hole. Those dust particles that you see, those are the light. That means those dust particles are seen. Why? Because light has entered inside through that particular aperture. Okay, so that phenomenon is known as diffraction. Now, diffraction is defined as the bending of waves around the corners of the obstacle or through an aperture into the region of geometrical shadow of the obstacle or aperture. So it means if it is incident upon an opaque object, it moves around the corners of the object, creating a shadow. If it enters through a slit or an aperture, it is able to move as a beam of light through the aperture, whereby it could penetrate into the other side of the aperture. Types of diffraction. We have Fraunhofer's diffraction and we have Fresnel's diffraction. Before I go into those, which I'll just give you a brief account, you do not have to know all these. So I'll just show you what diffraction looks like. Now, as you can see from this particular diagram, you will see that here, this is the light wave. That light wave is going to move across this aperture. This is a slit. Now this slit, what will happen is the light is going to squeeze itself through the aperture, but as it moves outward away from the aperture, it tends to increase in size. So the new wave over here, the new wave from radiating from the slit. Why radiating? Why? Because from here it has to squeeze itself, because there's only a small space given for the light to move. But the moment it exits from that particular slit, it tends to radiate out. This is also an example of diffraction. Okay, this is also an example of diffraction. This is when you using some obstacle on it and allow the light to pass through with a small aperture, so you'll see the light how it's coming out of the aperture. Now, before we come into this diffraction, Fraunhofer's and Fresnel's diffraction, I will just give you a brief explanation of those. Now, Fraunhofer's diffraction occurs with plane wave fronts when with the object effectively at infinity. Okay, so just know the names. Actually, you don't have to know why it's occurs, because I will not go into detail because we're doing only the basics. And Fresnel's diffraction is produced when light from a point source meets an obstacle. The waves are spherical and the pattern observed is a fringe image of the object. Okay, fringe image means a blurred image of the particular object. Okay, so when you see like a shadow is not the actual image of the object, but however you can see that it is means the corners are the shape of the object. So that is just what it is says, that is a fringed image of the object. So that is why when Fresnel's diffraction occurs, it is due to the obstacles, and when Fraunhofer's diffraction occurs, it is due to the passing of through the slits. Okay. Now we come to another phenomenon, polarization. Now, polarization is a property of a wave that can oscillate with more than one orientation. Okay. Now, we will see what is polarization. Now, polarization is defined as a phenomenon caused due to the wave nature of electromagnetic radiation. When I talk over here as electromagnetic radiation, now we are considering that light is also an electromagnetic wave. Okay. Now, when you see the electromagnetic spectrum from the previous topic that I have done, that means visible light also falls under the category of electromagnetic radiation. So that means is defined as a phenomenon caused due to the wave nature. We have know that light is a wave as well as a particle. So the wave nature of light will make it undergo this phenomenon of polarization. Light is an interaction of electric and magnetic fields that we know. Why? Because it's an electromagnetic wave traveling through space. The electric and magnetic vibrations of light wave occur perpendicular to each other. Okay, this we will do later on when you do electromagnetic theory later on in microwaves and stuff. We will understand how the movement of light waves occur. Okay. The electric and magnetic vibrations can occur in numerous planes. Numerous planes means many planes. It's not that it moves, because when you see light comes from all directions. It's not that it's confined to any direction, unless of course there is something to guide it. It is confined to one direction. But as long as there is no obstacle, no guiding, no wave guide that is able to guide it to a particular direction, it can move anywhere. So when it moves anywhere, automatically each single strand of light is an electromagnetic wave. Now each electromagnetic wave have got electric and magnetic fields, and due to the particular fields, numerous planes are generated because many light in all directions. So that means for every light that is being sent, there is numerous electric and magnetic planes. A light wave that is vibrating in more than one plane is known as unpolarized light, because it's free, nothing to guide it, it's free. So obviously it's unpolarized light. Polarized waves are light waves in which vibrations occur in a single plane. Now when there is something that is able to guide it, to make it move in one plane, then we say that that particular light is polarized. Okay, otherwise the free light that we see everywhere all around us, that is unpolarized light. Until and unless we contain that light to move in a particular direction, that is known as polarized light. So polarization is caused due to the electromagnetic radiation of light, and it's a property of wave that can oscillate is a property of the wave that can orient itself in one particular direction. Okay, the process of transforming unpolarized light into polarized light is known as polarization. Okay, so how will we transform? Let us see. The types of polarization that are present are linear polarization. When I say linear polarization, from the name itself, what does it mean? Means straight line. Okay. So when an ordinary light is reflected from a polarized surface or transmission through certain materials, the electric fields oscillates along a straight line. The electric fields that are generated oscillates along a straight line or in one plane. So the light is said to be linearly polarized. So if the electric fields are moving only in one plane or in a single line, that means they are linearly polarized. Then you have circular polarization. Now the electric field of light consists of two linear components that are perpendicular to each other. That means what are they? The magnetic as well as the electric field. Now the electric field of light also consists two linear components that are perpendicular to each other, which are equal in magnitude and have a phase difference of pi by 2. Now the resulting electric field rotates in a circle. So when there's a phase difference between the two fields that are occurring in the electric field, two different fields that are created, the components of the electric field. So when they are in the ratio of pi by 2, the resulting electric field rotates in a circle. Okay. Now when it rotates in a circle, so obviously it will look as if the resultant wave is moving in a circular direction. That is why it is known as circular polarization. Now depending upon the direction of rotation, it can be called left polarized or right polarized. If it's rotating in the clockwise direction, that means it's a right polarized light, or if it's rotating in the anti-clockwise, it means a left circularly polarized light. Okay. Then we have the next one, elliptical polarization. Elliptical polarization means the resulting combination of the particular components will generate a resultant wave of an ellipse. So the electric field of light describes an ellipse. Describe means the electric field shows that it is moving in the shape of an ellipse. This results why? Because from the combination of two linear components having different amplitudes of phase difference that is not pi by 2. For circular, they have same amplitude and a phase shift of pi by 2. But here we have two different amplitudes but not pi by 2. Okay. So that is why an ellipse light or an ellipse shape will be generated. Okay. That is why it's known as elliptically polarized light. Now when you look over here, I'm just going to show what polarization is. Okay. Now look over here. This is the light. Okay. This is light that is unpolarized. That means moving in all directions. Okay, moving in all directions. Here also one plane, here also one plane, here also one plane, here this plane, that plane. It's moving everywhere in all directions. But when you pass through this particular light, you pass through a filter or polarizing filter. Okay, you will see over here that it's moving in one direction. Exactly here in the form of a sine wave. Okay, this is polarized light. Okay. This is polarized light that is moving along a particular direction, means straight this side. Okay, this is linearly polarized. That is why. Otherwise, when you look at this unpolarized, you'll see all these lights are moving in different directions. Now we come to the next part, that are photons. What are photons? Light is composed of particles called photons. Okay. Now photons are particles of light. Now we know the nature of light is behave as a wave, that is an electromagnetic wave, and also as a particle. That means these are the particles of light called photons. A photon is a tiny particle that comprises waves of the electromagnetic radiation. That means each wave is composed of tiny particles of photons. A photon is also defined as a quantum of energy. That means a packet of energy. Okay. How a photon is produced? Now, you know, we have done in physics, you have done in chemistry, the electrons revolve around the nucleus. Okay. So consider the same type of setup for a photon. Electrons circle the nucleus in fixed orbits, that you know. An electron has a natural orbit that it occupies, but if you energize an atom, you can move its electrons to a higher orbital. That means if external energy is provided to a particular atom, what happens? It tends to give more energy to the electrons to move. Okay, because electrons are the ones that are moving around in orbits. So when you give an extra energy to the atom, the electrons will gain more energy. And due to their gaining in energy, okay, what will happen is they tend, because the energy is increased, they tend to move on to the next level or to a higher orbit of energy. Okay. Now, however, if this particular energy gets reduced after they have jumped over to the next level and it gets reduced, what happens is the energy decreases in that electron and it tends to fall back in its original level. So a photon is produced whenever an electron of a higher orbit falls back to its original orbit. So when it falls back, see, it has already obtained extra energy due to the external energy provided to the atom. Okay, it jumps over. It goes to the higher energy and goes there. Now when the energy starts to decrease, that it cannot remain in that particular energy level anymore, it tends to fall down. When it falls back to its original level, it releases a small amount of energy. That released energy, that constitute a photon. Okay. During the fall from high energy to normal energy, the electron emits a photon or a packet of energy. That's why we call a packet or a quantum of energy. Now look at this particular diagram. What you see over here is, can you see here? This is the higher orbit. This is the lower orbit. When external energy is provided, okay, when external energy is provided, this atom jumps over to the next level, right? Now when this gets reduced, somehow it cannot retain because it's just an external energy from somewhere, not its own. So obviously it cannot retain that energy. Due to that, it cannot remain in that orbit because that particular orbit has a specified level of energy. So it cannot remain, so it falls back to its original level. But a small amount of extra energy is still left with it. So when it falls back, it releases a small amount of energy in the form of a light particle. This is your light particle, that is a photon. So when it falls back, it releases the extra energy that it has obtained. Okay, that extra energy will form a light particle known as a photon. Okay, now the energy of a photon. The energy of a photon is given by E equal to HF, which is equal to hc by lambda, because we know HF is F is equal to c by lambda, because the frequency is always inversely proportional to the wavelength. This is the wavelength, this is the frequency, this is the speed of light in vacuum. This is known as a Planck's constant, which is given by 6.3 into 10 to the power minus 34 joules second, or the actual value is 6.626 into 10 to the power minus 34 joules second. You can take this value, 6.626 is fine enough. Okay, then F is the frequency of the photon, then C is the light, velocity of light in vacuum, that is 3 into 10 to the power 8 meters per second. Lambda is the wavelength of the photon. Okay, so those are the energy of a photon. Now we come to other formula for energy of a photon. Let us see what are the other formula. When dealing with photons, a commonly used unit of energy is electron volt rather than the joule. That means how we will find the energy of the photons in terms of electron volt. Okay, whatever you have just shown just now, that energy is generated in terms of joule, but now we will generate the energy in terms of electron volt. An electron volt is the energy required to raise an electron through 1 volt. Thus, a photon with an energy of 1 electron volt is equal to 1.602 into 10 to the power minus 19 joules. Okay, so if at all you get a value of this in electron volt, you have to convert in joules to joules. Okay, convert to joules. To find the photon energy in electron volts using the wavelength in micrometers, the equation is approximately given as E in terms of EV. EV means electron volt, equal to 1.2398 by lambda in micrometers. Okay, that means you have to convert later on, if at all you require, you convert everything into joules. The value of E represents the difference of the energies of two energy levels, that means delta E, when an energy goes through the excitation. So that means when you look at it in a particular energy level, you have high energy orbit, low energy orbit. So when that extra energy is provided to the atom, the extra energy is fed to the electron, where it obtains high energy and it jumps to the higher level. Okay, now If that energy gets decreased, it falls back to its original level, releasing a photon of light, right? But when you look at it in terms of energy, the high energy, it releases what? It goes to a high level, it comes back to a lower level. That means these two levels have their set values of energy. So when it releases the extra energy, right? So what is the extra energy? Isn't it the energy gap between the two levels, the high and the energy and the higher energy level and the lower energy level? Okay, due to that is why it is denoted by delta E. Delta E is the energy gap, the energy level, the difference of energy levels between the high energy and the low energy. Okay. The value of lambda corresponds to the wavelength of the emitted spectral light. Spectral light. Okay, so we can have another formula. Lambda is equal to hc by delta E. Okay, that means when you look at it, delta E is equal to E. Sometimes in certain books also, instead of writing E, they write as EP. EP means energy of a photon. Okay, delta E is equal to EP. So when you reverse this particular formula, you will see it comes back to the original value of energy of a photon. E is equal to HF. Okay. Okay, this is another assignment I'm going to give you. The energy gap between the radiating upper and lower levels is 0.8052 eV. Now see, this is given in eV. So you'll have to convert it into joules and you'll continue to do the problem. Now light in fiber optic is radiated at a wavelength of 850 nanometers. This is nanometers, 10 to the power minus 9. Calculate the corresponding frequency and energy of the single photon. First of all, find the frequency by using lambda is equal to C by F, and then use E is equal to HF to calculate the energy of the photon. Okay, so submit your assignment on time so that I can correct on time and grade you. Thank you.